In this lecture, we move into Module 5, Theory of Inference Procedures for Two Populations. In this module, we'll be investigating techniques for making inferences about two population variances, about two population means, and about two population proportions. In particular, we'll be looking at ways of comparing each of these parameters across two populations. Now, the first topic we'll look at will be inferences about two population variances, specifically hypothesis tests for two population variances, as well as point and interval estimation for the ratio of two population variances. Now, the reason we look at comparing the variances of two populations first is because what we know, or what can reasonably be assumed about the variances of two populations will determine or dictate how we go about comparing the means of those two populations. And so the assumptions and sampling framework for making inferences about two population variances. So we're going to have two samples, one sample from each of our two populations. For sample 1, let's denote the random variables comprising that sample using the letter x. So we'll let x1, x2, and so forth up to x sub n1 be a random sample of size n1 from a normally distributed population, the mean of which we'll denote by mu sub 1, and the variance we'll denote by sigma squared sub 1. Then let's use the letter y to denote the observations in sample 2. And so let y1, y2, and so forth up to y sub n sub 2 be a random sample of size n sub 2 from a normally distributed population with mean mu2 and variance sigma squared sub 2. And then finally, the two samples are assumed to be drawn independently of one another. So in other words, these are not paired samples. These are stochastically independent samples. And then finally, we are subscripting the sample size, and that is because we're going to allow the sample sizes to be different. There's no reason that the sample sizes would need to be the same. All right, and then so for each of the two samples, we can calculate summary statistics. And so we'll let x bar, s1 squared, and s1 denote the mean, the variance, and the standard deviation, respectively, of sample 1. And then we'll let y bar, s squared sub 2, and s sub 2 denote the mean, the variance, and the standard deviation, respectively, of sample 2. Now, let's consider this random variable given by s1 squared over sigma squared sub 1 and s2 squared divided by sigma 2 squared. It can be shown that under these assumptions that we've just stated, that this random variable has an F distribution with n1 minus 1 numerator degrees of freedom and n2 minus 1 denominator degrees of freedom. Now, that fact is going to be the basis for developing procedures that allow us to compare the variances of two populations, both via hypothesis testing as well as confidence interval estimation. And so let's first consider the following set of hypotheses. The null hypothesis is that the variance of population 1, sigma 1 squared, is less than or equal to rho 0 times sigma 2 squared. So the variance of population 2 times this quantity rho sub 0 versus the alternative, which would be, again, the opposite of that statement, the alternative that says that sigma 1 squared is greater than rho sub 0 times sigma 2 squared. And we're going to perform this test at a significance level of alpha. And again, just as by way of review, you'll recall that the alpha is the probability of a type 1 error. That's the significance level of the test. It's the probability of rejecting the null hypothesis when in fact the null hypothesis is true and should not be rejected. Now notice that, so what we're doing here The alternative hypothesis, remember we put what we're wanting to prove or show in the alternative hypothesis. And so what we're trying to show here apparently is that the variance of population 1 is greater than some multiple of the variance of population 2. And note that that multiplicative factor could be less than 1, it could be 1, or it could be greater than 1. And the value that we use will depend on the particular problem that we're looking at. Certainly, rho sub 0 has to be positive. It can't be a negative. It wouldn't make sense to have 0 or a negative number there. So rho 0 is a positive number. And again, depending upon the problem, it could be less than 1, equal to 1, or greater than 1. But regardless of whatever the value of rho is, what we're trying to show here, what we're looking to see is there's this significant evidence to prove or to conclude is that the variance of population 1 is greater, specifically greater, than this multiplicative constant times the variance of population 2. Now, if we note that what we can re-express these hypotheses in terms of the ratio of the two population variances. Specifically, if we divide both sides of the inequality in each of these hypotheses by sigma 2 squared, then we get hypotheses stated in terms of the ratio sigma 1 squared over sigma 2 squared. And so, having done that, the null hypothesis becomes that sigma 1 squared over sigma 2 squared is less than or equal to rho sub 0, versus the alternative that sigma 1 squared over sigma 2 squared is greater than rho sub 0. Now, you'll recall that the variance of a random sample is an unbiased estimator of the variance of the population from which the sample was obtained. And so S1 squared is an unbiased estimator of sigma 1 squared. And in addition, sigma 2 squared is an unbiased estimator of sigma 2 squared. And so it seems reasonable to base our inference on the random variable or a random variable that mirrors the function of the two parameters that we are testing a hypothesis about, right? And so it makes sense to at least consider basing the inference on the random variable S1 squared over S2 squared. Now, in order to base an inference on that random variable, we need to know something about the behavior of that random variable. In other words, and specifically, how does the ratio of the two sample variances behave under the conditions of the null hypothesis, and how does the ratio of the sample variances behave under the conditions of the alternative hypothesis? Once we determine that, can we use differences in behavior of S1 squared over S2 squared under the null and alternative hypotheses to come up with a way of discriminating between when the null and alternative hypotheses are true? Now, if the null hypothesis is true, then the ratio S1 squared over S2 squared will tend to be smaller than rho sub 0, the hypothesized value of the ratio of the population variances. On the other hand, if the alternative hypothesis is true, then S1 squared over S2 squared will tend to be larger than rho sub 0. And so this indicates that large values of the ratio of the sample variances, S1 squared over S2 squared, give evidence against the null hypothesis and therefore for the alternative hypothesis. The question is, how large does the ratio S1 squared over S2 squared have to be in order to reject the null hypothesis? Well, again, as usual, we're going to answer that question by looking at probabilities involving the ratio of S1 squared over S2 squared. And so we know, based on what we've stated previously, about the sampling distribution of the ratio of the sample variances, we know that if the null hypothesis is true, then S1 squared over S2 squared, the probability of S1 squared over S2 squared being less than or equal to rho sub 0 times the upper alpha percentage point of an F distribution with n1 minus 1 numerator degrees of freedom and n2 minus 1 denominator degrees of freedom is equal to, that probability is equal to 1 minus alpha. The probability that the ratio S1 squared over S2 squared is greater than that value, rho sub 0 times this F value, by the complement rule is equal to alpha. And so these probability statements lead to the following acceptance and rejection regions. And so for this right-tailed test, if we want to call it that, the acceptance region would be the interval from the 0 up to and including rho sub 0 times the F value that we've got listed here. All right, so this interval is obviously open on the left but closed on the right. And so this acceptance region consists of the set of values of the ratio S1 squared over S2 squared that are consistent with the null hypothesis and lead to its acceptance at a significance level of alpha. The complement of this set, the complement with respect to the positive part of the real line, so it is the open interval from rho sub 0 times this F value, the upper alpha percentage point of this F distribution, up to, but certainly not including infinity, but including all real numbers greater than this lower bound. All right, that comprises the rejection region. And this is the set of values of the ratio S1 squared over S2 squared that are inconsistent with the null hypothesis and therefore would lead us to reject the null hypothesis at a significance level of alpha. Now we can restate this in terms of decision rules. And so we would accept this null hypothesis if the test statistic S1 squared over S2 squared is less than or equal to rho sub 0, the hypothesized value of the ratio of the variances, times this upper alpha percentage point of the appropriate F distribution. And we would reject the null hypothesis if the ratio of the sample variances is greater than that critical point. And so we could also think in terms of plausible and implausible regions for the ratio of the population variances, and that would so they would be defined in this way. The plausible region would be the interval with lower endpoint given by the ratio of the sample variances, S1 squared over S2 squared, divided by the upper alpha percentage point of the appropriate F distribution, and then going out to positive infinity. And this would be the set of plausible values for the ratio of the population variances, sigma 1 squared over sigma 2 squared, in the sense that the null hypothesis would not be rejected in favor of the alternative for any value of rho sub 0 in this interval based on the observed value of the ratio of the sample variances. The complement of that set, the complement with respect to the positive part of the real line, would be the interval, the open interval from 0 up to this point. And so based on the observed value of the ratio of the sample variances, the null hypothesis would be rejected in favor of H1 for any value of rho sub 0 in that interval. Now let's consider the next test we'll look at. So the null hypothesis being that the variance of population 1 is greater than or equal to some hypothesized value rho sub 0 times the variance of population 2 against the alternative that sigma 1 squared is less than that quantity. And so again, we can restate this in terms of the ratio of the population variances. And so in doing that, the null hypothesis is that the ratio of the population variances, sigma 1 squared over sigma 2 squared, is greater than or equal to rho sub 0 against the alternative that says that that ratio of population variances is less than rho sub 0. And so again, we want to consider how does the ratio of the sample variances behave under the two hypotheses, and we want to use differences in behavior to come up with some rejection criteria. And so in this case, if the null hypothesis is true, then the ratio of the sample variances, S1 squared over S2 squared, will tend to be larger than rho sub 0, this hypothesized ratio of the population variances. And by the way, we're using rho as the hypothesized or the notation to represent this hypothesized ratio because of the R sound, obviously, ratio and rho. Okay, so anyway, on the other hand, if the alternative hypothesis is true, in other words, if the ratio of the population variances, sigma 1 squared over sigma 2 squared, is less, something less than rho sub 0, then S1 squared over S2 squared will tend to be smaller than rho sub 0. And so then, intuitively, small values of S1 squared over S2 squared give evidence against the null hypothesis and for the alternative. Again, the question is, how small does the ratio of the sample variances, S1 squared over S2 squared, have to be in order to reject the null hypothesis? So again, we determine this or answer this using probabilistic considerations. And so by definition of the upper 1 minus alpha percentage point of the F distribution with the appropriate numerator and denominator degrees of freedom, based on the definition of that quantity, the probability that S1 squared over S2 squared being greater than or equal to rho sub 0, the hypothesized value of that ratio of population variances, times this F value, this probability would be equal to 1 minus alpha. And so by the complement rule, the probability that the ratio of the sample variances is less than that value is alpha. And so these probability statements lead to the following acceptance and rejection regions. The acceptance region for this test would be the set of values with lower endpoint, the interval of values from with lower endpoint of the interval given by rho sub 0 times this F value, which again is the upper 1 minus, it's the 1 minus alpha upper percentage point of this F distribution. So all values on the real line greater than or equal to that value. So this is the set of values of the ratio of the sample variances that are consistent with the null hypothesis and lead to its acceptance at a significance level of alpha. The complement of that set, and again the complement with respect to the positive part of the real line, so this would include the interval, the open interval, it's open on both sides, from 0 up to rho sub 0 times this upper 1 minus alpha percentage point of this F distribution. The rejection region is given by that interval, and this is the set of values of the ratio of the sample variances that are inconsistent with the null hypothesis and therefore would lead to rejection of the null hypothesis at a significance level of alpha. Again, we can restate this in terms of decision rules. All right, and so we would accept the null hypothesis if the ratio of the sample variances, S1 squared over S2 squared, is greater than or equal to rho sub 0 times the upper 1 minus alpha percentage point of this F distribution. We would reject the null hypothesis if the ratio of the sample variances is less than that value, rho sub 0 times the upper 1 minus alpha percentage point of the appropriate F distribution. We can restate each of these decision rules in terms of a rho sub 0, and so we would we would accept the null hypothesis for any value of rho sub 0, or if the value, the hypothesized value rho sub 0 is less than or equal to the ratio of the sample variances divided by the upper 1 minus alpha percentage point of this particular F distribution. We would reject the null hypothesis if the hypothesized value of rho sub 0 were greater than that quantity, the ratio of the sample variances divided by the upper 1 minus alpha percentage point of the appropriate F distribution. We can take the second bullet point in each of these, in the acceptance and rejection rules, to come up with plausible and implausible regions. And so the plausible region is the set of plausible values of the ratio sigma 1 squared over sigma 2 squared, in the sense that the null hypothesis would not be rejected in favor of the alternative for any value of rho sub 0 in that interval based on the observed value of S1 squared over S2 squared. All right, and so you can see here the interval that gives the plausible region. And the complement of that set would be the implausible region. So based on the observed value of the ratio of the sample variances, the null hypothesis will be rejected in favor of the alternative for any value of rho sub 0 in that particular set. And then finally, let's consider the following test. The null hypothesis being that sigma 1 squared is equal to rho sub 0 times sigma 2 squared, against the alternative that sigma 1 squared is not equal to rho sub 0 times sigma 2 squared. And we're going to perform this test at a significance level of alpha. This test is equivalent to testing the following hypotheses, which we obtained from the previous hypotheses just by, again, dividing both sides of the equation by sigma 2 squared. All right, and so the null hypothesis would be that sigma 1 squared over sigma 2 squared is equal to rho sub 0, against the alternative that says that sigma 1 squared over sigma 2 squared is not equal to rho sub 0. And so again, how does the ratio of the sample variances behave under the conditions of the null hypothesis? How does the ratio of the sample variances behave under the conditions of the alternative hypothesis? And then we want to use differences in behavior of the ratio of the sample variances in the two situations to help us come up with rejection criteria. And so if the null hypothesis is true, then the ratio of the sample variances, S1 squared over S2 squared, will tend to be close to the hypothesized ratio of the population variances, which is denoted by rho sub 0. On the other hand, if the alternative hypothesis is true, so that the ratio of the population variances is not equal to this hypothesized value, then the ratio of the sample variances will tend to be farther away from rho sub 0 than it is when the null hypothesis is true. And so this indicates that values of S1 squared over S2 squared that are far away from rho sub 0 provide evidence against the null hypothesis and therefore for the alternative hypothesis. And so the question is, how far away from rho sub 0 does the ratio of the sample variances have to be in order to reject the null hypothesis? And so again, using what we know about the sampling distribution of S1 squared over S2 squared, we know, and also based on the definition of these F values, notice that here on the left-hand quantity, we have the upper 1 minus alpha over 2 percentage point of the F distribution with the appropriate degrees of freedom. And the quantity in the right-hand side here, inside parentheses, is the alpha over 2 upper percentage point of this F distribution. And so based on the definition of these quantities, we know that the probability of observing a value of the sample, a ratio of the sample variances, if the null hypothesis is true, we know that the probability of observing a value of this ratio of sample variances between these 2 points is 1 minus alpha. And so therefore, by the complement rule, the probability of observing a value of S1 squared over S2 squared less than this lower point or greater than this upper critical point are alpha. And so these probability statements lead us to the following acceptance and rejection regions. All right. And so we would accept the null hypothesis. Well, let me state it in terms of an acceptance region, which goes from this lower endpoint up to this upper endpoint. And notice again that the lower endpoint has this f value, which is the upper 1 minus alpha over 2 percentage point of the f distribution. And the upper endpoint here is the upper alpha over 2 percentage point of the appropriate f distribution. And so this set of values, this is the set of values for the ratio of the sample variances that are consistent with the null hypothesis and therefore would lead to its acceptance at a significance level of alpha. The complement of that set, which is the union of these two intervals that you can see here, this is the set of values of the ratio of the sample variances that are inconsistent with the null hypothesis and therefore lead to its rejection at a significance level of alpha. We can restate each of these in terms of decision rules. And so we would accept the null hypothesis, in other words, fail to reject the null hypothesis, if the ratio of the sample variances is between these two values that we've got listed here. And we would reject the null hypothesis and conclude that the alternative is true if the ratio of the sample variances is either less than this lower critical point or greater than this upper critical point. And we can also restate each of these rules, the acceptance and rejection rules, in terms of rho sub 0, the hypothesized value for the ratio of the population variances. So we would accept the null hypothesis if the hypothesized value of rho, the hypothesized value of the ratio of the population variances, is between these values, so s1 squared over s2 squared divided by the upper alpha over 2 percentage point of the appropriate f distribution, or if it's less than or equal to the ratio of the sample variances divided by the 1 minus alpha over 2 upper percentage point of this f distribution. We would reject the null hypothesis if the hypothesized value rho sub 0 is either less than this quantity here or greater than that quantity. And so if we consider the second bullet points under for both the acceptance and rejection regions, then we come up with plausible regions. All right, and so again, the plausible region here consists of the set of plausible values for the ratio of the population variances, in the sense that the null hypothesis would not be rejected in favor of the alternative for any value of rho sub 0 in this interval given here based on the observed value of the sample variances s1 squared over s2 squared. The complement of that set is the implausible region, and so that is the this is based on the ratio of the sample variances, and we know that the null hypothesis would be rejected in favor of the alternative for any value of rho sub 0 in that interval. And so let's put all this together and come up with our hypothesis testing procedure. And so we have three sets of hypotheses, which I'll denote A, B, and C as usual. And as usual, we could consider hypothesis A to be the hypothesis for a two-tailed test. We could consider hypothesis B to be the hypothesis for a left-tailed test. And then we could consider hypothesis C to be the hypothesis for a right-tailed test. Now, I've stated each of these sets of hypotheses both in terms of the ratio of the population variances, but also in terms of having each population variance on one side of the relationship here, as you can see. Now, let me just say that in many situations, in many hypothesis testing situations, the value for rho sub 0, the hypothesized value for the ratio of the population variances, in many situations that will be 1. But it doesn't have to be 1. But in many situations, it will be 1. But just keep in mind that you need to base the value that you use for rho sub 0 on the problem at hand. So there may be situations where you want to use a value of 2 or maybe 1.5 or something like that. So you just need to consider the particular problem at hand and to choose the value for rho sub 0 that is meaningful and useful for that particular situation. All right, and so the test statistic that we'll use will be the ratio of the sample variances, and we're going to call this F-calc. We'll call it F-calc because we're going to get the critical points from the F distribution. The sampling distribution of this test statistic under the conditions of the null hypothesis. The test statistic has an F distribution, and in particular, it's got an F distribution with numerator degrees of freedom given by n1 minus 1 and denominator degrees of freedom n2 minus 1. And so the rejection criteria for a two-tailed test will be to reject the null hypothesis for either small values of the test statistic or large values of the test statistic. In particular, if F-calc is less than rho sub 0 times the 1 minus alpha over 2 upper percentage point of the F distribution with the appropriate numerator and degrees of freedom, or if F-calc is greater than rho sub 0 times the upper alpha over 2 percentage point of the appropriate F distribution. For a left-tailed test, we're going to reject the null hypothesis if F-calc is less than rho sub 0 times the upper 1 minus alpha percentage point of the appropriate F distribution. And we will reject, for a right-tailed test, we'll reject the null hypothesis if F-calc is greater than rho sub 0 times the upper alpha percentage point of the F distribution with the appropriate degrees of freedom. Now, let's talk briefly about the F distribution and the F table. And there are actually several F tables. There is an F table for each upper tail area that we're talking about. And so the F tables in the back of our notes or on the website, let's put it that way, are somewhat limited because of the nature of the F distribution. And they do not include values with upper tail areas for P where P is greater than 0.1. So for example, the tables do not provide the value for the upper 0.95 percentage point of the F distribution for any combination of numerator and degrees of freedom. And again, and so this seems like a limitation, but the reason that this is the case is because we can obtain this kind of an F value, this percentage point, using this relationship here. So what this is telling us is that the upper P percentage point of an F distribution with numerator degrees of freedom given by df1 and denominator degrees of freedom df2, that is equal to 1 over the upper 1 minus P upper percentage point of the F distribution with numerator degrees of freedom df2 and denominator degrees of freedom df1. So note that, for example, if P is equal to 0.95, well, that's what we're showing down here. One thing I want to point out here is that in this relationship, notice that we have to switch the order of the degrees of freedom. So the numerator degrees of freedom on the left-hand side become the denominator degrees of freedom on the right-hand side, and the denominator degrees of freedom on the left-hand side become the numerator degrees of freedom on the right-hand side. And so, for example, even though the tables don't include the upper 0.95 percentage point of the F distribution with 5 numerator and 10 denominator degrees of freedom, that value can be obtained from the 0.05 F table by dividing by 1 the upper 5th percentage point of the F distribution with 10 numerator and 5 denominator degrees of freedom. All right, and so that would be end up being 0.2110. This is the table, the F or the file containing the different F tables that are available on Moodle. And so let's find this value. So we want to compute the upper 0.95 percentage point for the F distribution with 5 numerator and 10 denominator degrees of freedom. According to this formula, that's equal to 1 over the upper fifth percentage point of the F distribution with 10 numerator and 5 denominator degrees of freedom. So we need to first look in the 0.05 F table, and we need to find the corresponding F value. And so notice that this on the first page in the F table, that's the 0.1 table. So we need to scroll down, and here we have the 0.05 F table. Now we need the upper fifth percentage point for the F distribution with 10 numerator degrees of freedom and 5 denominator degrees of freedom. Notice that the columns here correspond to the numerator degrees of freedom, and the rows correspond to the denominator degrees of freedom. And so we want 10 numerator and 5 denominator degrees of freedom. And so the upper fifth percentage point for that F distribution is 4.74. So that's how we get that. And then when we divide 1 by that 4.74, we get 0.2110. So the reason that we don't have tables for upper percentage points that are, or for upper tail probabilities that are greater than 0.1 is because we can get those from the existing tables that we do have using this formula. And so we could use that relationship to find at least some of these values here. So here we have the upper 0.975 percentage point for the F distribution with 14 numerator degrees of freedom and 9 denominator degrees of freedom. In the next one, we have the upper 0.99 percentage point for the F distribution with 5 numerator and 2 denominator degrees of freedom. We then want to find the upper 0.9 percentage point for the F distribution with 8 numerator and 12 denominator degrees of freedom, and so forth. And so we could use the relationship and the existing F tables to find these F values. And so I would encourage you to find these on your own, practice, and make sure you can do this. But I would point out that we're not able to find this one because we don't have a table that's got 50 numerator degrees of freedom. If we look at the F table, we see that it only goes up to 30 numerator degrees of freedom. All right? And so we are not able to use this relationship to find this particular 0.975 percentage point. Okay, so we know that if we had such a table that we could find that, but we can't do it because the table does not have the large enough numerator degrees of freedom. But one way to get around this is to use SAS, and so let's see how we might do that. And so here is some SAS code that we can use to find this 0.975 percentage point directly without actually having to use that relationship. We can just find it directly. All right, and so this SAS code, and I'll let you read through this, will give us the upper 0.975 percentage point for the F distribution with 25 numerator and 50 denominator degrees of freedom being equal to 0.48107. Now, you can use this code to find any value, any upper percentage point for an F distribution. All you would have to do is to change the numerator and denominator degrees of freedom to what they need to be, and then change Q, the value for Q, which is the desired upper tail area, change that to whatever value you want. And so I would encourage you to play around with this SAS code and just make sure that you can not only get this value, but use it to obtain these values directly. All right? You can obtain each of these values without having to use this relationship. You can get these values directly using that SAS code. Now let's look at some examples. So we'll go back to our example where we're filling this process, this production line, where we're filling jars with peanuts. And so filling the jars with peanuts, we not only want the average weight of the contents to be 8 ounces, but we also want to maintain a degree of consistency in the amount of peanuts being dispensed into jars. Now, management is considering installation of a new control device that increases the consistency, in other words, reduces the variability of the output of the machine, or so says the producer of that new control device. Now, before purchasing it, management wants to test the device to determine whether it will indeed reduce the variability. Now, to test the device, a sample of 11 jars is examined from a machine without the device. We'll call that population 1. And a sample of 9 jars is examined from a machine with the device installed, and so we'll call that a sample from population 2. The data from the experiment are given in table 5.5 in the text, and also, well, on the next slide. And figure 5.4 shows side-by-side box plots for the data. So that's from the textbook from which I got this example. But what we want to do is using a 0.05 level of significance. Is there sufficient evidence to conclude that the device reduces variability? So let's see how we can answer that question. And so here are the data. We have sample 1. This is a sample of jars of peanuts from the machines without the new control device. We have a sample size of 11 jars of peanuts. The sample mean, the weight of the peanuts in the jars, was 8.2291 ounces, and the standard deviation, S1, was 0.2824. The second sample, this is the sample from the machines that do have the new control device. The sample size for this sample is 9. The mean is 8.1011, and the sample standard deviation, S2, is 0.1304. Now, the question is, does the new control device reduce the variability of the fill weights of the peanuts that are being dispensed into jars? And we can see here that there does appear to be some evidence of that. The variance of sample 2, the variance of the fills, the sample variance of the fill weights from the machines with the new control device is quite a bit less than the sample standard deviation of the fill weights from the machines without the device. But you know, it's difficult to determine just by looking at it whether or not that's a big enough reduction at the significance level we're going to be testing this at to actually conclude that the new device actually does reduce variability. And so what we need to do is formally perform the test. And so we'll let a sigma 1 squared be the variance of the weights of peanuts dispensed by the machine without the new control device. And we'll let sigma 2 squared be the variance of the weights of peanuts dispensed by the machine with the new control device. And so the hypotheses to be tested are given by the following. And it is perhaps easier to come up with these hypotheses by first considering them not as a ratio, but just with a variance on either side of some relationship. Now, based on the definition of sigma 1 squared and sigma 2 squared, what we're wanting to try to prove, we're looking to see if there's sufficient evidence to conclude that sigma 1 squared is greater than sigma 2 squared. In other words, if the variance of weights of peanuts dispensed by the machine without the new control device is greater than the variance of the weights of peanuts being dispensed by the machine with the new control device. You would agree that if this is true, then the new control device does reduce the variability of the fill weights. All right. Now we can re-express this relationship in terms of a ratio of the population variances by dividing both sides of this inequality by sigma 2 squared. And so the corresponding alternative hypothesis would be that sigma 1 squared over sigma 2 squared is greater than 1. The opposite of that, the null hypothesis, would be that the ratio of the population variances, sigma 1 squared over sigma 2 squared, is less than or equal to 1. Equivalently, that is the null hypothesis, that sigma 1 squared is less than or equal to sigma 2 squared. So in this particular situation, because we're only interested in the qualitative relationship that sigma 2 squared is less than sigma 1 squared, we haven't stated by how much less, just whether it's less, then because of that, the hypothesized value for rho sub 0 is 1. And so this is an illustration or an example of what I was saying before, that in many situations, the hypothesized ratio will be 1. But again, it could be that the management would say, look, we only want to purchase this new device if it cuts the variability in half. And so if that's the case, then the hypothesized value would not be 1, but it would be 2. And so, in that case, then, you would use the 2 here in this. But we're in these hypotheses. But this is for this particular example, the hypothesized ratio value to use is 1. Now, the formula for the test statistic, again, is the ratio of the sample variances. And because this is a right-tailed test at a significance level of 0.05, the critical point is the upper fifth percentage point of the F distribution with 10 numerator and 8 denominator degrees of freedom. And so again, we will reject the null hypothesis if F calc, the value of our test statistic, which is the ratio of the sample variances, is greater than 3.35. Another way to think about this is we're going to reject the null hypothesis if the variance of sample 1 is more than 3.35 times bigger than the variance of sample 2. Now, to calculate the value of the test statistic, we need to go back and obtain the summary statistics from the data. So we have remember that these are sample standard deviations. So this is the standard deviation of sample 1 and 0.2824, and the standard deviation of sample 2 is 0.1304. And so in calculating the value of the test statistic, we need to be sure to square those values, and we get 4.688. Now, because FCalc 4.688 is greater than our critical point, 3.35, the rejection criteria have been satisfied, and so we reject the null hypothesis and conclude that the ratio of the population variances is greater than 1. In other words, we conclude that sigma 1 squared is greater than sigma 2 squared. And so there is sufficient evidence at the 0.05 level of significance to conclude that the new control device reduces the variability of the output of the machine. Now let's look at how to come up with confidence limits for a ratio of population variances. And again, recall that the random variable, S1 squared over sigma 1 squared, divided by S2 squared over sigma 2 squared, has an F distribution with numerator degrees of freedom given by N1 minus 1 and denominator degrees of freedom given by N2 minus 1. Because of this, and based on the definition of the this upper alpha percentage point of the F distribution with those numerator and denominator degrees of freedom, the probability that this random variable takes on a value less than or equal to this upper alpha percentage point is 1 minus alpha. We can rearrange the quantities inside the parentheses to get an expression involving the ratio of the population variances all by itself on one side of the inequality. And so that gives us the probability that sigma 1 squared over sigma 2 squared being greater than or equal to this random variable being equal to 1 minus alpha. And so this implies that in repeated sampling, the random variable given by the ratio of the sample variances over the upper alpha percentage point of this F distribution will be less than or equal to sigma 1 squared over sigma 2 squared 1 minus alpha times 100% of the time. We can restate that by saying that sigma 1 squared over sigma 2 squared will be greater than or equal to that random variable, again, 1 minus alpha times 100% of the time. And so the random variable given by the ratio of the sample variances divided by the upper alpha percentage point of the F distribution with the appropriate degrees of freedom, this is a 1 minus alpha times 100% lower confidence limit for the ratio of the population variances sigma 1 squared over sigma 2 squared. Now, once calculated, we say that we are 1 minus alpha times 100% confident that the ratio of the population variances is greater than or equal to this lower confidence limit. Similarly, we can come up with the probability that this random variable is greater than or equal to the upper 1 minus alpha percentage point of the F distribution. That probability is 1 minus alpha. And so again, we get a probability statement involving this random variable here, S1 squared over S2 squared divided by the upper 1 minus alpha percentage point of this F distribution being greater than or equal to the ratio of the population variances. And those probabilities are equal because the events are equivalent, and so that probability is 1 minus alpha. And so this implies that in repeated sampling, the random variable given by the ratio of the sample variances divided by the upper 1 minus alpha percentage point of the F distribution with the appropriate degrees of freedom will be greater than or equal to this ratio of the population variances 1 minus alpha times 100% of the time. Equivalently, the ratio of the population variances sigma 1 squared over sigma 2 squared will be less than or equal to this random variable, again 1 minus alpha times 100% of the time. And so because of all that, we call the random variable, or the random variable given by the ratio of the sample variances over the 1 minus alpha upper percentage point of this F distribution, that random variable is a 1 minus alpha times 100% upper confidence limit for the ratio of the population variances. And so once we've calculated that, once we have our two samples, and we've calculated this random variable, this upper confidence limit, then we say that we are 1 minus alpha times 100% confident that sigma 1 squared over sigma 2 squared is less than or equal to this upper confidence limit. And then finally, if we take what we've learned about constructing a lower confidence limit and an upper confidence limit, and we compute a 1 minus alpha over 2 100% lower confidence limit and a 1 minus alpha over 2 times 100% upper confidence limit. And so notice that we're dividing alpha by 2 in each of these. Okay? If we put those two confidence limits together, we get a two-sided 1 minus alpha times 100% two-sided confidence interval for sigma 1 squared over sigma 2 squared. And so this would be the formula then for a two-sided confidence interval that has a confidence level of 1 minus alpha times 100%. So those are the formulas for constructing confidence limit, a lower confidence limit all by itself, an upper confidence limit by itself, and then a two-sided confidence interval. And we see how we are constructing these confidence limits using probability considerations based on the sampling distribution for the random variables that we're using, in particular this random variable here. Okay, and so once we've constructed this two-sided confidence interval, we can say, the way that we interpret this is that we say that we are 1 minus alpha times 100% confident that sigma 1 squared over sigma 2 squared is somewhere in this interval. And so let's look at an application of this. Again, going back to this situation where we're filling jars with peanuts, and the company is considering installation of a new control device that increases the consistency by reducing the variability of the output of the machine. However, before purchasing the new control device, management wishes to test the device to ascertain whether it will indeed reduce variability. Now, to test the device, a sample of 11 jars is examined from a machine without the device, so that's a sample from what we'll call population 1, and a sample of 9 jars is examined from a machine with the device installed. That's a sample from what we'll call population 2. The data were given, so we saw the data back on our previous slide, and so what we want to do is compute the appropriate 95% confidence limit that can be used to answer this question. So remember, so here's the data again replicated so that we can see it again and refer to it easily. Now, because the hypothesis test that we used to answer this question was a right-tailed test using a significance level of 0.05, then the appropriate type of confidence interval will consist of a lower confidence limit by itself, and it will in particular be a 1 minus alpha, so 1 minus 0.05, so 0.95 times 100%, so a 95% lower confidence limit for the ratio of the population variances sigma 1 squared over sigma 2 squared. And so the formula for the 95% lower confidence limit for the ratio is given by this formula, this expression here. The ratio of the sample variances, S1 squared over S2 squared, divided by the upper fifth percentage point of the F distribution with 10 numerator and 8 denominator degrees of freedom. And again, notice that going back and looking at the summary statistics for the two samples, the size of sample 1 is 11, and so we've got 10 degrees of freedom associated with that sample. And then the size of sample 2 is 9, and so we would have 9 minus 1, or 8 degrees of freedom associated with that sample. And because sample 1 variance is in the numerator, sample 2 variance is in the denominator, we've got 10 numerator degrees of freedom and 8 denominator degrees of freedom. And that percentage point, all right, so going to the 0.05 table, and we've got 10 and 8 degrees of freedom respectively. And so here we have the upper fifth percentage point for the F distribution with 10 numerator degrees of freedom and with 8 denominator degrees of freedom, so 3.35. Okay, and so when we do the calculation, the 95% lower confidence limit is then found to be 1.3995, or about 1.4. So we can be 95% confident that the ratio of the population variances, sigma 1 squared over sigma 2 squared, is at least 1.3995. Now, another way to say that would be to multiply both sides of this inequality by sigma squared, and so we can be, we're 95% confident that the variance of population 1, the variance of the weights of peanuts being dispensed by the machine without the control device, is at least 1.3995 times larger than the variance of the fill weights by the machine with the new control device. And so if all we're looking for is sigma 1 squared being greater than sigma 2 squared. Because 1.3995 times sigma 2 squared is strictly greater than sigma 2 squared, then we could draw that same conclusion that we were able to make using the hypothesis test. But notice that not only can we draw that same conclusion that we made with the hypothesis test, we actually have more information here because now we've actually quantified the how much bigger sigma 1 squared actually is than sigma 2 squared at a particular level of confidence. Now let's look at another example. So mesquite is a thorny bush whose presence reduces the quality of pastures in the southwest United States. In a study of growth patterns of this plant, dimensions of samples of mesquite were taken in two areas of a ranch. The two areas of the ranch are labeled A and M. So we are interested in determining whether the average heights of the plants are the same in both areas. To perform the test for a difference of means, so let me just back up a second. Ultimately, what we're interested in is comparing the means, the average heights of the plants in the two areas. But in order to perform that hypothesis test, in order to know how to proceed through that and actually perform that test, we need to know something about, we need to determine what's reasonable to assume about the population variances, the variances of those two areas on the ranch. And so to perform the test for a difference of means, we will first need to know whether the variances of the two populations of plant heights are different, or whether it is reasonable to assume that the variances of the heights of mesquite in the two areas are equal. So is it reasonable to assume that the variances of the heights of plants in the two areas on the ranch are equal? If that's the case, then we can use one procedure for comparing the means, the mean heights of the two plants across the means of the plants across the two areas. On the other hand, if it's not reasonable to assume that the variances are equal, then we would need to use a different procedure. And so here are summary statistics. We're not going to have the actual raw data for this, but we do have summary statistics for the two samples. And so the summary statistics for what we'll call sample A are given here. And I actually don't like this notation. I'm going to modify the subscripts. I'm going to call sample A, we'll call that sample, that will correspond to a sample from population 1. And I'm going to change the subscripts to denote that. And then we'll do the same down here. These will be for, we'll refer to these as sample 2. Okay, so I've modified the notation a bit to keep it consistent with the way that we've been denoting these things in the notes. And so again, what I'm calling sample A, I'll also refer to that as sample 1. And the sample from area M in the ranch, I'll refer to that as sample 2. And so we have our summary statistics for sample 1, the sample size, which is 20. And so we've got 19 degrees of freedom associated with that sample. And then notice that the standard deviation of sample 1 is 0.5155. The size of sample 2 is 26, and so we've got 25 degrees of freedom associated with that sample. And the standard deviation of sample 2 is 0.3751. So not a big difference here, although it's probably, I guess, about 1 point. The standard deviation of sample 1 is about 1.5 times bigger than the standard deviation of sample 2. But is that difference big enough for us to conclude that the underlying population variances are different? Well, we need to perform the test in order to answer that question. So we're going to perform this test using a 0.05 level of significance, and in addition, construct a 95% confidence interval estimate for the ratio of the population variances. Okay, so let sigma 1 squared be the variance of the heights of mesquite trees in area A of the ranch, and then sigma 2 squared be the variance of the heights of mesquite trees in area M. And so with that, the hypotheses to be tested are given by the following. what we're trying to do, what we're trying to show, look to see, is there sufficient evidence to conclude that the variances of the heights of mesquite trees in the two areas are different. And so remember that we always put what we're trying to show in the alternative hypothesis. So the alternative hypothesis would be that sigma 1 squared is not equal to sigma 2 squared. Now, when we're testing hypotheses about variances, we're going to restate those in terms of a ratio. And so this would be equivalent to sigma 1 squared over sigma 2 squared being not equal to 1. The alternative the opposite of that, which is the null hypothesis, would therefore be that the ratio of the population variances is equal to 1. And of course, that is equivalent to the null hypothesis that the population variances are equal. Okay, so the formula for the test statistic is again going to be the ratio of the sample variances. And then to determine the rejection criteria, we note that this is a two-tailed test, right? And the significance level that we're going to use is 0.05. And so the rejection criteria are to reject the null hypothesis if F-calc, our test statistic, the ratio of the sample variances, is either less than 0.40971 or if it's greater than 2.3184. Now, I've gone back in and modified that just a little bit to list these critical points to the kind of precision that we have in our current F table. And so the rejection criteria would be to reject the null hypothesis if F-calc is less than 0.410 or if it's greater than 2.32. Now, the F statistic is equal to 0.5155 squared over 0.3751 squared. And so we get 1.8887, or we could round that to 2 or 3 decimal places if we wanted to. But since that value is not less than 0.410 and it's not greater than 2.32, the rejection criteria have not been met. And so we fail to reject the null hypothesis. And so we can conclude then that there is insufficient evidence at the 0.05 level of significance to conclude that the variances of the heights of mesquite trees differ in the two areas. Now, another way to say this, because why did we do this? Why are we looking at the variances? Why are we comparing the variances of the heights of mesquite trees or mesquite bushes in the two areas? Because ultimately what we're wanting to do is proceed to a comparison of the population means. And so while we have not proved the null hypothesis to be true, and that's a good point to make. Whenever we fail to reject the null hypothesis, we're not proving that the null hypothesis is true. All we're doing is failing to reject it. But what this is telling us is that it's not unreasonable, as we proceed to the comparison of the means, it's not unreasonable for us to assume that the population variances are equal. All right? And so when we go to that subsequent analysis to compare the means of the populations, we can use a procedure which assumes that the population variances are equal. All right? Because again, at the 0.05 level of significance, we fail to reject the null hypothesis that the population variances are equal. Right? It's reasonable. It's not unreasonable to make that assumption as we proceed to the subsequent analysis. Now, let's also construct the appropriate type of interval. And because the hypothesis test, to answer this question, is a two-sided confidence test, two-sided hypothesis test, and because the significance level was 0.05, the corresponding type of confidence interval would be a two-sided 95% confidence interval. And so to construct that, we construct a 97.5% lower confidence limit, a 97.5% upper confidence limit, and then when we put those two confidence limits together, the interval that we obtain is a 95% two-sided confidence interval. And so we can be 95% confident that the ratio of the population variances, sigma 1 squared over sigma 2 squared, is somewhere between 0.8147 and 4.6098. And because, notice that 1 is in this interval. Because 1 is in this interval, we know then that we cannot rule out the possibility at this level of confidence. We cannot rule it out that sigma 1 squared over sigma 2 squared is equal to 1. In other words, we cannot rule out the possibility that at this level of confidence, we cannot rule it out, the possibility that sigma 1 squared is equal to sigma 2 squared. So again, we can answer the same kind of question using a confidence interval that we can with a hypothesis test. But along with the confidence interval, we also get more information, quantified information, about the range of values that the parameter, or in this case the function of the two parameters, the ratio of the population variances, can take on. So that is the end of the material that we're going to be looking at on making inferences about two population variances, specifically comparing the variances of two populations using hypothesis tests and also using confidence intervals. The next topic will be inferences about two population means, but we're going to do that in the next lecture video.